Laboratory. In this video, we will see the determination of a transfer function of higher order systems with two or more subsystems. Coming to the title, determination of a transfer function of a higher order system with two or more subsystems. That means here we are by using the block diagram. By using block diagram, we are finding the transfer function. That means in block diagram having two or more subsystems and how to find the overall gain, overall transfer function. It means obtain the transfer function for a given block diagram which consists of two or more systems by using simulation. So already in class means we will solve by block diagram reduction techniques. By using block diagram reduction techniques, we are finding the overall gain transfer function of a system. The same way how we are writing the coding part we will see now. So already if we observe the block diagram, here we are having a three blocks are there. G1, three blocks are there. G1, G2, G3, three blocks are there. And now what is G1 means S plus 1 by S square plus 2S plus 3 is the G1 block gain. Coming to the G2 block gain S plus 2 by S plus 4 and G3 block is S plus 1 by S plus 3. Totally we are having three blocks, they connected in different fashion and block gains also they mention. So coming to the first step, first we will complete the theoretical calculations and then we will see how to write the coding part and how we are getting the simulation, whether both are same or not, we will observe. Coming to the theoretical calculations means by using the block diagram reduction techniques. By using block diagram reduction techniques, we will find the transfer function, that means overall gain. If you observe the block diagram, what is the first step where we will start the simplification means G1 and G3. These two are in parallel. The signal starts from here and travel towards the summing point. And here also is starting and G3 and then again ending at the same point. So these two blocks are in parallel. G1 plus G3 are in parallel. So already we know the G1 and we know the G3. By substituting and if simplifying, we will get a one transfer function. That one we are assuming as a, if we reduce these two blocks, parallel blocks, then we are assuming we are getting a transfer function y. And now after reducing this one, this y and G2 are in, this transfer function y and G2 are in series. This y and G2 are in series. Already we know the y and already we know the G2. If we substitute and if we simplify, then we are getting a one more transfer function. That one we are assuming as a y1. That means after reducing the y and G2 block, that is a series blocks, we are getting a y1 transfer function. If now we are having a total this one called y1, and now if you observe, this y1 is having a feedback path. Y1 is having a feedback path. So if you eliminate this y1, we are getting a final transfer function. That only call it as an overall gain. That is the overall transfer function for the block diagram that we need to calculate now. Coming to the theoretical calculation part, that is G1 and G3 are in parallel. So these two blocks are in parallel. If we reduce, then we are getting this the transfer function. That means if we substitute the G1 and G3 values and simplify the equation, then we are getting s cube plus 4s square plus 9s plus 6 by s cube plus 5s square plus 9s plus 9. So this is the first step reduction. By reducing the parallel blocks G1 and G3, and now this combination and G2 are in a series. This total combination is in a series with G2. So this combination is this one and G2 are in series. So now we need to reduce the series of blocks. Now already we know the G2 and already this one. If we substitute and simplify, then you are getting s power 4 plus 6s cube plus 17s square plus 24s plus 12 by s power 4 plus 9s cube plus 9s square plus 45s plus 36. And now if we observe these total blocks, we reduce it, and that one we are assuming as a sum transfer function of y1. So now this y1 is having a feedback path. So if we eliminate this feedback, If we eliminate this negative feedback path, then we are getting a overall gain of the system. That is the overall transfer function. So that means eliminate the unity feedback. Eliminate the unity feedback, then we are getting the final transfer function as a s power 4 plus 6s s cube plus 17s square plus 24s plus 12 by 2s power 4 plus 15s cube plus 46s square plus 69s plus 48. So this is the final transfer function. This is the final transfer function. This is the theoretical calculation part. And once if it is over, now we will see the coding part, how you are writing the coding part for the same block diagram to get the final transfer function. Coming to the apparatus required, you need a personal computer and a MATLAB software. Previously, how we are solving the theoretical calculations, the same sequence you need to write the programming part also. That means here we are having a three blocks are there. That block gains G1, G2, G3 is there. So first we need to insert this G1, G2, G3 values into the system, into the MATLAB. So we need to enter the G1 transfer function, G2 and the G3. Then how we are solving previously parallel of blocks. First we are eliminating the parallel of blocks and then a series and then feedback. In the same sequence you will write the coding part. So first coming to the G1, first coming to the G1, here we are having a numerator and denominator. So first you need to specify the numerator. So coming to the numerator part, here the highest power is s power 1. So s power 1 coefficient. S power 1 coefficient is 1 and s power 0 coefficient is also 1. So numerator equal to 1 space 1. So this is the numerator part. And coming to the denominator part, here the highest square is s square. So s square coefficient is 1 and s power 1 coefficient is 2. S power 0 coefficient is 3. So denominator coefficients are 1 space 2 space 3. So this is the denominator coefficients, 1 space 2 space 3. And once if we know the numerator and denominator, we are framing the G1 transfer function. That is G1 is equal to TF of numerator comma denominator. So with this we know the G1 function. With this we know the G1 block gain. Now we need to specify the G2 block gain. Coming to the G2, again we are having a numerator and denominator. So first numerator 1. S power 1 is the highest power. So S power 1 coefficient is 1. S power 0 coefficient is 2. So coming to the numerator 1. Coming to the numerator 1, NUM 1 space 2. S power 0 coefficient is 1. S power 0 coefficient is 2. So NUM 1 is 1 space 2. And next coming to the DEN1. DEN1. Coming to the DEN1, here also S power 1 is the highest power. So S power 1 coefficient is 1 and S power 0 coefficient is 4. So DEN1 is equal to 1, 4. 1 space 4. So once if you know the numerator and denominator of the G2 transfer function, we'll frame that one. So G2 equal to TF of numerator 1 comma denominator 1. TF of numerator 1 comma denominator 1. So this is the G2. And now we need to specify the G3 function. Need to specify the G3 function. Coming to the G3, here also need to specify the numerator and denominator. Numerator is s plus 1, so s power 1 is the highest power. So s power 1 coefficient is 1 and s power 0 coefficient is 1. So numerator 2 is equal to 1 space 1. Numerator 2 is equal to 1 space 1. This is the numerator 2 coefficients. And coming to the denominator, here also s power 1 highest power. So s power 1 coefficient is 1 and s power 0 coefficient is 3. So DEN elements are, that is the 1 space 3. DEN2. Once if we know the numerator 2 and denominator 2, that is the G3 block gain. So we can frame the G3 block. So G3 is equal to TF of numerator 2 comma denominator 2. G3 is equal to TF of numerator 2 comma denominator 2. Now with this the block gains, we know the block gains G1, G2, G3. Now, depending on how they are connected, based on that, we will write the coding part. Right. Now, if you observe that G1 and G3 are in parallel, so we need to reduce the parallel of blocks. If we reduce this one, we will get a one transfer function. That one we call it then y. We are taking a variable y is equal to parallel of G1 and G3 blocks. Parallel of G1 comma G3 blocks. This is the first step. And now if you reduce this one, you are getting a transfer function y, and this y and G2 are in series. This one, if we are reducing, then we are getting a transfer function y. And now this y and G2 are in series. So next reduction will be the series of blocks y and G2. Here we are getting a one more transfer function that we are assuming as a y1. So y1 is equal to series of y comma G2. This is the second step. The second step. And now if we reduce this complete one, that one, if it, that means parallel blocks you reduce it, series blocks you reduce it, then we are getting a transfer function y1. So this y1 block having a feedback loop. Now we need to eliminate this unity feedback loop. So there we are getting a final transfer function, that one we are assuming as a y2. So y2 is equal to feedback of y1 comma unity feedback, so 1. Feedback of y1 comma 1. With this, the last step, this will give the overall transfer function. Last step will give the overall transfer function for the given block diagram. Previously we did theoretically by using the block diagram reduction techniques. The same sequence how we are doing the same sequence you are writing the coding part. This is the coding part. Now we will see in MATLAB software. Yeah, we will open a new script. That means editor. Here we will enter the program. Okay, already in slide program is there. Directly I will copy and paste the programming part. Same program I'm copying. Same program I'm copying and pasting in the editor script. Yeah, program is there. And the first line will prefer CLC. It will clear the previous data. Anything is there in command window. And if we run means it will show the current output only. Next is the programming part. And now we will save and we'll run the program. We'll see how we are getting the transfer functions all step by step. Yeah, we need to save the file. Let it be the same name. Yeah. Here graph and all nothing is there, so that all data it will come in command window only. We'll see in the command window what and all it's coming. Yeah. Coming to the first one, numerator 1 1 we give and denominator as a 1 2 3. Then we are getting the transfer function G1, that is s plus 1 by s square plus 2s plus 3. This is the G1 block gain. Is the G1 block gain. And next NUM1 we gave as a 1 2 and DEN1 is the 1 space 4. So G2 block, we are getting the G2 block with a gain s plus 2 by s plus 4. This is the second block gain. Second block gain s plus 2 by s plus 4. And the next NUM2 1 space 1, DEN2 1 space 3. Now by using these two, we are framing a G3. There is a G3 gain is s plus 1 by s plus 3. S plus 1 by s plus 3. This is the G3 block gain. With this, the 3 block gains, everything is there. Now based on the connections, that means based on whether parallel or series, step by step we are writing the coding part and we are finding the transfer function. So coming to the first step, what is the first step? What is the y we are assuming? If we are observing the program where we are having the y, the 11th line of the program, here we are having a y. This y is equal to parallel of G1 comma G3. So if you reduce the parallel blocks, you are getting a transfer function. That one we are assuming as a y. So That is the y. That means G1 and G3 blocks are in parallel. So if you reduce the parallel blocks, this is the transfer function you are getting. S cube plus 4s square plus 9s plus 6 pi, s cube plus 5s square plus 9s plus 9. This is the first simplification, parallel of blocks. And next y1. What is y1? This one simplification and the G2 blocks are in series. The simplification and G2 blocks are in series. If you reduce that one, then that one you are assuming as a y1. That one you are assuming as a y1. So that is the s power 4 plus 6s cube plus 17s square plus 24s plus 12 by s power 4 plus 9s cube plus 29s square plus 45s plus 36. So this is the second step reduction. Previous parallel blocks and G2 are in series. So if you reduce this one, this is the transfer function what you are getting y1. It's the transfer function y1. And if you observe now, we are having a main block y1 forming a unity feedback path. So now we need to eliminate the unity feedback path. That is the final transfer function. That is the final gain of the system, overall gain of the system. So that one we are taking as a y2. So here y1 having a unity feedback path. So feedback of y1 comma 1 will give the y2 transfer function. That means we are eliminating the feedback path and we are getting a final transfer function as a s power 4 plus 6s cube plus 17s square plus 24s plus 12 by 2s power 4 plus 15s cube plus 46s square plus 69s plus 48. So this is the final transfer function what you are getting. The same thing already we did by using block diagram reduction techniques. Already we did by using block diagram reduction techniques. Now the same block diagram we are writing a coding part and we are getting the same result. This is the coding part, how we are getting the result. Everything here, graph and all, nothing is there. So all the output data it will come in command window. You can verify step by step clearly at each and every step what is the final transfer function you are getting. Each and every simplification we can observe easily in MATLAB. And coming to the programming, the same program directly copied and checked, we are getting the same values only, same result only. And coming to the conclusion is that, so from the simulation we are finding the overall gain as a simulation overall gain as this one. That is the overall transfer function s power 4 plus 6s cube plus 17s square plus 24s plus 12 by 2 s power 4 plus 15s cube plus 46s square plus 69s plus 4. Previously block diagram reduction techniques, by using block diagram reduction techniques we are solving the same sequence the same way. We are writing the coding part and we are checking the overall transfer function in simulation software also. Thank you.